Hi. In this video, we're going to look at an example of an inelastic collision and how momentum can be conserved. So let's get started with this example. Noah gets bored in a grocery store and starts pushing an empty 15-kilogram shopping cart at an alarming speed of 8 meters per second down the grocery store aisle. He releases the cart and it runs into a display stand on wheels holding a wonderful array of Fig Newton bars, which has a mass of 24.0 kilograms. The grocery cart gets tangled with the display stand and they roll down the aisle as one jumbled mess, but somehow without any friction. Imagine that. How fast does the cart stand conglomeration travel? So, we always start these kinds of problems where there's two things colliding with a before and after sketch. So, as you try to solve problems like this, it's essential that you start with a sketch of the situation before and after so you can define what your system is and also figure out what direction things are traveling in, positive or negative. So, I've drawn the picture to show that the cart is moving to the right, so it's moving in a positive direction before colliding with the display stand. And then afterwards, they move together as one object to the right. So now I'm going to move myself up here a little bit, and I'm going to use our equation for momentum conservation, which says that the momentum of this system does not change from beginning to end. So whatever the total momentum is at the beginning, in other words, our total initial momentum, it will equal our total final momentum. So what is our total initial momentum? What is our total final momentum? Well, the initial momentum is going to be simply the momentum of the grocery cart plus the momentum of the display stand. So I'm just going to write that in mathematical terms. Momentum of the cart, so mass of the cart times the velocity of the cart, plus the mass of the display stand times the velocity of the display stand. So those are the two momentum added up beforehand. And I guess I should distinguish that this is the initial velocities rather than the final velocities. So I can write in my subscripts here a little comma and say the initial momentum. So this is the velocity of the cart initially and the velocity of the display stand initially. The masses don't change, so I don't worry about putting in the initial symbol for the mass. So what is the momentum at the end here? They're kind of acting as one object at the end. And so it wouldn't make sense to add up a momentum of both of them when we can simply just add up the mass times velocity of both of them together. And so to represent that mathematically, there are different ways you can do it. But the way that I typically do it is I say the mass of the cart plus the display stand and the velocity of the cart plus the display stand. So we're getting kind of messy with our subscripts here, but this is the best way to stay organized is to be as precise as possible. So I want to make sure we're clear about what we're saying in our math symbols. So now we can start substituting in some values. And to do that, we're going to look at our word problem originally here. So it looks like for the shopping cart, it's got a mass of 15 kilograms and an initial velocity of 8 meters per second. All right, the mass of the display stand, it says, was 24 kilograms. The initial velocity of the display stand, if you look at it in the picture, it should be clear that it's not moving, so the velocity is 0. Now, you might be someone who recognized that early on and you realize, okay, this whole term right here, 24 times 0, it's just going to disappear. 24 times 0 is 0. So you can, if you see that coming, you can just kind of cross it out and you know it's going to be 0. But I wanted to work it out for you here totally. Now, this is where the change happens. This is a little bit different of a step here because now we need to figure out what is the mass of the cart and the display stand together. So it's not simply just 15 or 24, but instead, if they're together, we're going to add their two masses together. So 15 kilograms plus 24 kilograms for the mass. And that's going to be multiplied by the velocity of the two together. Okay. So as we continue to work this problem out, 15 times 8, I should be able to do that in my head, but, speaking of my head, it's in the way. 15 times 8, 120 kilogram times meters per second plus 0. So this just is not there anymore. And then 15 plus 24, that's going to be a mass of 39 kilograms. All right, so the 0 is just gone. I'm going to erase it just to make my math a little bit more clear here on this next step, because now I need to solve for the velocity of the cart and display stand together. To do that, I'm going to undo the multiplication here by dividing by 39 kilograms. And because we have an equal sign, we got to do the equal thing to the other side of the equal sign to keep it equal. All right, that gets rid of the number in front of the velocity that we're looking for. But now we're going to do 120 divided by 39. That'll give us, we need two significant figures, so we're going to round that to 3.1. So 3.1, and the kilograms cancel out. We're left with meters per second for a unit, and that's going to be the velocity of the cart plus the display stand together. It is in the positive direction. It's still moving to the, in the positive direction. If you remember up here, the cart originally was going at 8 meters per second. So it slows down pretty substantially to 3.1 meters per second when it collides with the display stand. But this makes sense because now it's a larger mass. So to keep the same momentum isn't lost. It's going to go slower, but still have the same momentum before and after. So that's all I've got for you in this video. Remember, how you do anything is how you do everything.